All right. So, how are things going with the physics? I know last time we were talking about a homework question, the one about the balls that collide, and we were trying to figure out the system of equations. I'm curious first, did anybody figure out what them telling us how they collided does to help us?
I haven't gotten that far yet.
Okay.
I couldn't figure it out.
Did anybody get any divine inspiration? The physics god smiled upon you. You heard the, physics angels from on high. I'm going to take that as a no. No. Well, I want to circle back to that just to give you one more little push, because we are definitely going on the right track, but something about the way they hit makes it so that we don't have as many unknowns as we think we do. So let me go to the whiteboard and let me show you how we can approach this. So I don't have the specific numbers, and I'm not going to create the exact system, but I'm going to give you kind of the idea behind this. So we had the two balls that came together, and they were coming from whatever random directions they were coming. But because they ended up hitting exactly side by side, you can think of this collision as being just a horizontal collision, so that the verticalness doesn't change. Do you understand what I mean? Because as they're coming in like this, they hit directly tangent to each other on the side. So whatever they had going in the y direction is going to stay. The only change is in the x. So we had built some system, built a system of equations, and we had some things. But one more thing we can add in now is that the Vy initial is going to equal Vy final for both of these particles. So the next thing you know, we went from 4 unknowns down to 2 unknowns. And so we can use conservation of momentum in the x direction, and we can use conservation of energy if we assume that it's an elastic collision. So this is really the change, because they ended up hitting like that. Had it been oriented so that they made their collision like this way, so that they are exactly vertical, now all of the change is going to be in the y direction, and there's going to be no change in the x direction. If they ended up coming and hitting kind of off to the side, then we'd have to worry about both different components. So that's the extra little shove I'm going to give you today about this one, is just to realize that the verticalness of this, the y, doesn't actually get affected because of the fact that they impacted in exactly this way. So hopefully that makes sense, and hopefully that's a good little shove to help you finish that problem. So are there any of the other homework problems you want to look at, or anything out there that we need to talk about before we keep looking further into this rotational stuff? Okay, as always, I'm going to take silence as a nope, we're good to go. All right, so where we are, we've now gotten ourselves so that we have all these rotational quantities like angular momentum, angular acceleration, oh, sorry, not angular momentum, we're not there yet. Angular acceleration, angular velocity. We now have moment of inertia, which is basically playing the role of mass with rotation. It's telling us how resistant to rotation an object is. And so we looked at building the kinetic energy, and all these formulas are like identical to those that were coming from the linear, except for the fact that these are now angular quantities. So I want to do another example now that we kind of have this whole idea with the energy and everything, where we look at the the relationships between all these before we move on to the equivalent of force. Like, what is the thing like force in the rotational world? So let me go back to the whiteboard and we'll go ahead and do an example here.
Hey, Bruce, really quick. Can I ask you something? So,
Absolutely.
Larry is like giving us a lot of homework now.
Uh-huh.
So I'm just wondering, like, are the homeworks for physics gonna be different? Like, the due dates, are they gonna be different each week or what? Because I feel like we might need some time since we're also getting a lot of homework from other classes and stuff. And I feel like Larry won't really let us. I mean, he's just fixed on like what the amount of homework that he's gonna give us. So I don't know. I'm just wondering. You know.
Okay, so I put the due dates for all of the physics homework on Canvas. So if you go and you look the assignments that are there, they all have a due date attached to them. And so there is a due date. They vary depending upon where I think we're going to be when they come up. All right. So, but
Okay.
I will also tell you, because I mentioned this last time, that those dates are kind of placeholder dates because I don't know if we're going to speed up, slow down, and all that. And so I'm already planning on that we're going to have to adjust some of them anyway. So if we end up in a situation where you guys are getting really overwhelmed, and I know it's going to be calculus that's primarily the issue because I think looking at the list, everybody except for Ian is in first year calculus. So obviously, especially if there's like an exam coming up or something, just let me know. And you know I'm pretty flexible. Actually, you may not know because you've not been in physics with me and you've only had one class with me, most of you. But I'm fine with adjusting things a day or two, or giving you the individual, like if you're like, hey, can I have one more day? I'm not really a hard ass about homework because it's just homework and that's where you get your practice. And I want to make sure you get your practice, right? I'd rather you do that than just say screw it and not turn it in. So, but yeah,
Okay.
if something funky comes up, Max, you just let me know.
Okay. Yeah, I really appreciate that because I was getting worried because we have like a lot of homework this week, and so I was getting worried that maybe at some point we're not gonna be able to do the physics and stuff. But I, yeah, knowing that it's good for, like stress and stuff.
Yeah. And I also understand that that these are weird times. That's a weird situation. We got a lot of other stuff we're worrying about, not necessarily just school. So, hey, we're all in this together, as they say. So I don't mind doing my part, especially helping alleviate any of the stress that's not, necessary to be there. So don't stress out. Just communicate and let me know.
Okay, thank you. I appreciate that.
Yeah, you're welcome. Okay, well, let me go to the whiteboard and just kind of remind you of some of the things that we've talked about now in terms of angular quantities. All right, so first things first, in terms of just position now we're using theta, right? We're looking at angle. Think of this as the equivalent of x. So I'm going to write here our angular quantities in this left-hand column, and on the right, I'm going to write the linear equivalent. So we had angle, then we also had omega. So this is our angular velocity. So that's the equivalent of v. Then we had alpha, which is our angular acceleration. That's the equivalent of a. So those are the basics in terms of just kinematics. But then we moved on to, we have I. So I, this is our moment of inertia. And it really plays the equivalent of m. Okay, so it's very similar to the mass of the object. All right, so we've got all these new quantities. We also saw that kinetic energy kind of ended up taking on the same form. And the kinetic energy we saw was 1/2 I omega squared instead of 1/2 mv squared. And the moment of inertia, I also just kind of wanted to point out real quick that this was it's the sum of the MR squareds. And so what this is you take the mass of all the little individual particles and you multiply by the square of the distance away to the axis of rotation, and you add them up. It turns into an integral when we have some continuous object. I don't remember what I did. Did we do maybe the disk? I think we did the cylinder, right? As an example, but you can do a ring like like a wheel. You can do a rod. It can actually be anything that's rotating about something. And so again, notice that this is the same idea of kinetic energy of 1/2 mv squared. So far, everything has just been a direct replacement. And we're going to see that that continues today. But I want to show you an example of how we can use this to kind of solve an applied problem that tells us a little bit about what's going on. So here's an example. Let's say that we've got a flywheel. And a flywheel, this is just a huge mass, excuse me, that's rotating. And we use this to sort of store energy. I don't know if you've ever seen like a oil pump or something like that. It usually has like big masses in the back that are like rotating, right? That are big and heavy. And they kind of let the rotation continue. Well, that's the idea behind a flywheel. So let's say we've got a big flywheel, just a big circular disc, and we've got a radius of 1.2 meters. And the mass of this thing is 70 kilograms. So it's pretty large. Now, what I'm going to tell you here is that for a point on the end, we can have a maximum centripetal acceleration. This is designed in such a way that this material can only sustain this kind of stress. And so what we want is that outermost point to go at most, go fast enough so that at most it's got a centripetal acceleration of 3,500 meters per second. So centripetal acceleration, remember that's the one that points towards the center. So that's this piece trying to go in. Now you may ask, Bruce, is this actually a legit thing? And the answer is yes. Centripetal acceleration, if that gets too high, these pieces are going to want to fly off. So this is the kind of deal where you're spinning so hard that stuff on the end just can't stay together anymore, and it would cause your wheel to break apart. This is what happens with a lot of machinery as it gets older, when it starts breaking down, is that these pieces start losing their structural integrity. And so what they used to be able to handle, the forces used to be able to handle, but don't work anymore. So, but here's the situation. We want to get it so that there's a maximum centripetal acceleration of 3,500 meters per second squared. So here's what I want to know then. A couple of questions. First one is, what is the maximum omega allowed? And then a follow-up to that then is, what is the maximum rotational kinetic energy? And the maximum kinetic energy is going to happen when we reach that maximum omega, right? Because the biggest omega, that's going to make it so that we get the greatest kinetic energy. All right, so let's start with the first question. How do we figure out what the maximum omega is? Any ideas? Okay, so Victor just threw in the chat, we can use the centripetal acceleration. I think that's good. We definitely need to start there. So let's think about that. I didn't put up the formula here, but I gave it to you a bit ago. We know that the centripetal acceleration, it actually depends upon how fast we're spinning, right? And we also know that omega is related to velocity, linear velocity. So let's just put up some formulas. We know that AC is equal to v squared over r. So v is the linear velocity and r is our distance away. So anything moving in a circle has this kind of centripetal acceleration. So we know the 3,500 equals this. So we can actually use that to find v, because we also have r. But then there's also a relationship between v and omega, which is that v is equal to r times omega. So hopefully you remember that all the linear quantities are off of the angular quantities by a factor of r. So we can actually use both of these to convert this into something that will get us omega. So we're going to get AC is equal to r omega squared over r, which if I reduce that down is r omega squared. And I think that's where Victor was going. If you look in the chat, I think he just had the power on the r instead of the w. But we definitely know that this is the centripetal acceleration. So since we know a maximum AC, we also know our r. That's going to allow us to figure out what omega is. All right, so let's see. Omega then is going to be the square root of AC over r, which is the square root of 3,500 divided by 1.2. So we can do our computation with that. Crack out our calculator. I didn't actually do this one before, I apologize. And I get 54, basically, 54 and change. So this is around 54, and the units on this are radians per second. So that's the angular velocity. So in every second, it's going to do 54 radians. Do you guys have any idea how fast that is? Like, contextually, do you understand what that means? And it's okay if you say no.
I mean, it's probably really fast.
Probably. So here's what you could do. Probably the number that you would make, or would make more sense to you, would be rotations. So if we had a number that was just how many times we go around. Well, remember that in radians, one rotation is 2 pi. So if you divide that by 2 pi, that'll tell you how many times it's going around. And I just did that real quick and I got 8.6. So think about this. In 1 second, this wheel is spinning around 8.5 times. So yeah, Victor, I divided by 2 pi. All right, so it's going around about 8.5 times every second. You may also know RPMs, revolutions per minute. We use that a lot, like in automobiles and all that. You could do the same thing. You could convert that to minutes. All you'd have to do is multiply by 60. Now it would tell you how many radians per minute or how many revolutions per minute. So if you took 8.6 times 60, that's like 52.5 or something. Or sorry, no, 520 something. So it's going around about 525 times every minute. So pretty quick. It's not as fast as an engine, an automobile engine, but this is also considerably larger than anything that spins in an automobile engine. Okay, so we got part A. We figured out the maximum omega allowed. So now I want to know, what is the maximum rotational kinetic energy in the wheel?
So real quick before we start on B, I was canceling out my units, and I just want to be sure. The meters do cancel. Where does the radians come into play? Is it just the fact that we're rotating?
So radians are dimensionless. I'll hop in here so you can see. So radians are dimensionless. So in reality, there isn't anything on this. It's just a per second. But we put radians on there to kind of illustrate the fact that this is a rotational thing. It's not just a frequency. It's not just a hertz.
Makes sense. Thank you.
Okay, you're welcome. All right, so let's go to part B. How are we going to figure out the maximum rotational kinetic energy? Well, let's start with the formula. We know that the kinetic energy is going to be 1/2 I omega squared. So we just found omega. So we're going to be able to put that in and square it. But we also need to get I. We need to know what the moment of inertia is for this flywheel. All right, well, we're assuming that we're rotating about the origin, or the center of this thing, because otherwise setting this up with our R wouldn't have made sense. So we're looking for spinning about this axis. So that axis is going through the center of mass, so we don't have to worry about using that parallel axis theorem or anything like that. We just need to know the moment of inertia for a disk. Well, the moment of inertia for a disk is the same as for the cylinder, because you may remember that with our cylinder, the length didn't end up mattering. So whether this is just a thin flywheel versus like a huge cylinder, it still works out. And we found that this I think is the one that we calculated. It's 1/2 mr squared, where m is its mass and r is its radius. So that we can put in. We can go ahead and put those numbers in here for our I. So we're going to get 1/2 times 1/2 times 70 times 1.2 squared. Let's put the numbers on here. That's kilograms, that's meters. And then our omega, we've got 54. And that's just a per second squared. And if you look on the units of this, we're going to get kilogram meter squared second squared. And if you go back to joules, remember how we get joules? Those are the units because it's Newton meters. The Newton is a kilogram and one of these meters per second squared. So our units definitely match up. All right, so you go ahead and multiply those all together, and what you end up with is 73,500 joules. So if we get this thing spinning as fast as we possibly can, we're going to end up having that much energy just due to the rotation. And again, that's kind of the idea behind these, is you get a lot of energy stored in rotation that then could be used for other things. I know it's not potential energy, it's kinetic energy. And when I say it's stored in there, it's not potential energy, but it's energy that can be changed into another form, which could be moving a cable that then moves something else, or vice versa. All right, so there's an example of how we can use this to actually do some energy calculation and find out what's going on. So any questions on that one? Alrighty. So we have one more big thing to cover in terms of rotation, and that's the equivalent of force. So what is it that acts like force when it comes to rotation? So if you think about what forces do, those are the pushes and the pulls. And those are the things that actually cause acceleration, right? We've got Newton's second law, good old F equals ma. So what we need is something equivalent that causes angular acceleration. So what we're going to have to do, we're going to create, well, we're going to name it. These are the things that actually cause rotations to speed up or slow down, right? I mean, that's what forces do. Forces take objects and either slow them down or speed them up, depending upon which way they act. Well, same thing here, except it's not a linear motion anymore, it's now rotation. So we're either going to make the rotation happen faster or have the rotation happen less, right, slower, depending again upon the direction of the alpha. All right, so what this is called torque. So let's jump to the board here. So the equivalent of force in rotation is called torque. It's T-O-R-Q-U-E. So torque. So again, what these things do, these cause angular acceleration. So think about it. Suppose that I have something that I want to spin. So I've got like a bike wheel. Let's say it's stationary. What could I do to actually make it start spinning? Like, think about it.
Apply a force to it.
Okay, so I'm gonna have to apply a force, right? Like if I just wanted to spin this, I could maybe brush my hand down across the side. In fact, let me crack out my rotating object here. Okay, so here's the ball that we're gonna use to rotate. If I wanna make this thing spin, I do have to apply a force, right? I put my finger on here and I apply a force. And you can all see how I'm doing it. I'm kind of like pulling it. I'm using friction to help me do it. But I apply a force, it starts to spin. So I actually applied torque. Now, after I started spinning, it eventually stops. So it slowed down, which means there was another torque being applied. That one was being applied by frictional forces, whether it's the friction between the ball and the pen, the air in the ball, or something like that. So torque comes from force. It's related to force. They do go together. All right, so here's that example. Let's say this is the wiffle ball, right? So we got our holes here and you're seeing it spin around. But I applied a force this way. And what that ended up doing was causing this to rotate. So torques come from forces. And here's the way that it's defined. It is a cross product. It is a vector. And it's found by crossing R and F, where F is our force. And then R is what we call the moment arm. Sometimes it's also called the radial arm, depending upon who you are. But they're the moment arm or the radial arm. So that vector, where that vector happens to be, is it comes from the axis of rotation and it goes out to where the force was applied. So I was applying the force right here on the ball. So that's where this R is going to be. So that's how we define it. It's the cross product of R and F. So you may remember that we ran into the cross product when we were talking about omega. So let me just remind you, with cross products, this guy, the torque. Oh, and this, just so you know, is the Greek letter tau, T-A-U. So it's a little curvy T, That's a tau. So it's the cross product. It's going to be perpendicular to both R and F. So in my picture here, R and F are both in this plane. They're both in the whiteboard. So the cross product is going to be either be coming out of or into the board, just like we saw with omega the other day. Ralph, this is a lowercase tau. The uppercase tau looks like an uppercase T. So that's actually the lowercase tau.
What's the R again? I can't really see it because my internet just bad
Okay,
quality.
we call it the moment arm or the radial arm, and it's a vector that goes from the axis of rotation, so where I'm spinning it, to where I'm applying the force.
Okay.
So if we go back to this with the wiffle ball here, so here's our wiffle ball. R would go from the center of the pen up to where I was applying the force, which was at the top of the ball. So just be aware that it doesn't come from the tip of the pen. It's just like the straight distance down to the axis. So it's actually inside of the ball right now, but it would stick out this direction. And then the force vector is being applied this way because I'm pulling it towards me. If I went the other direction and I gave it a push, my R would still be pointing like this, but my F would be pointing the other direction. Is that good? Does that make sense, Max?
Yeah.
Okay.
Yeah, thank you.
All right, so this one, in terms of whether it points into the board or out of the board, again, is which direction is it rotate? So let me show you the right hand rule again. So using your right hand, I'm going to use the like curling thing, where I'm going to put my palm even with R, and then I'm going to curl it towards F. So let me redraw this. I'm going to put the two vectors together. So here was my force vector, and here was my R vector. It's still pointing the same direction, I just moved it up. And then hopefully you remember that about vectors, is that their location doesn't matter. Where they actually start doesn't matter. It just matters what direction they're pointing and how long they are. So I'm going to line my hand up with R, and I'm going to curl my fingers towards F. And notice that makes my thumb come out of the board towards you. And so that's where the torque vector points. Now, the easy way to figure this out is actually imagine that you're grabbing the axis of spin. Okay, so we're going to grab the axis of spin. And then you want to put your fingers in the direction of the force vector. Okay, so I'm grabbing this force vector. And you notice how my hand kind of curls in this direction, like it's going to go counterclockwise. That's the kind of rotation I'm going to get. So just imagine grabbing that axis, and then wherever your thumb is pointing, if it points in the direction of torque, just follow your fingers, and that's what kind of rotation you'll get. So if my force went the other way, it would want to spin clockwise, and now my picture would look like this. So we'd have R and F. Again, put my palm in the direction of R. I need to curl towards F, so I got to turn my hand over. And as I curl towards F, my thumb is pointing in the other direction. So that's going to cause a clockwise rotation. All right, so that's how you can tell which direction tau points. And also will tell you what direction of rotation you're going to get from that torque. Okay, or if not rotation, that change in the angular velocity. So I was causing that angular velocity to increase this way, so it started spinning. If you want just the magnitude of this, there's a nice little formula. So the magnitude of the torque, just how long that vector is, it's actually found by taking the magnitudes of the two vectors. So the length of your moment arm, how far away you're applying that force, and how large the force is. You multiply those together. And then you also multiply by the sine of theta, where theta is the angle between R and F. So for ours, the theta was 90 degrees because they were orthogonal to each other. But let me just show you an example where they're not necessarily. So let's say those are R and F. Then we need to know what this theta is. So this is how we're going to calculate our torque. We're just going to multiply the force by how far away it is from the axis, and then make sure we multiply by the sine of the angle in between them. So in the example I was talking about, spinning the wiffle ball, when that force was exactly perpendicular to R, then the sine is equal to 1, because the sine of pi over 2 is equal to 1. And that's actually the biggest we're going to get. The torque is biggest when the force applied is perpendicular to the moment arm. And it's going to be smallest. Sine of theta is going to equal 0 when those two things are in line, when there's an angle of 0 or 180 degrees, so they're pointing opposite direction. So let me talk about this a little bit in terms of application, stuff we want to turn. So one of the best examples for turning things and showing you this is actually a door. Hold on one second here. Victor just asked a question. So R is always the same magnitude but different direction. What do you mean by that, Victor? Because R is going to be just the distance away from the point of rotation to where we're actually applying a force. And so it's R. And in terms of direction, it's always written as going out from the axis to the place where we're applying the force. Did you maybe mean, instead of R, did you mean the torque? Okay, so the angle, here's kind of the cool thing about this angle. When I drew those before, like this was my R and this was my F. And I just realized you couldn't see the board. Hold on one second. So when we had this was my R and this was my F, it turns out it doesn't matter whether we're talking about this angle or if I had R going this way, and we talked about that angle, call it phi. It turns out it absolutely doesn't matter. If you remember from your trig, these would be your first quadrant and your second quadrant angles that have the same reference angle. And in the first and second quadrant, the sine is the same. So you end up getting the same number either way in terms of the magnitude. And this magnitude formula, this one that I gave you right here, it doesn't take into account which direction the torque is going. So whether it's coming out or in, that you just have to pay attention to looking at the picture and figuring out what way it's going to rotate. So like looking at this picture, I would immediately go, oh, this is going to cause rotation in a counterclockwise direction, which means this is my resulting vector. But you can see that if you were to draw R and F and then do the right-hand rule. But in terms of the actual calculation, it doesn't matter which angle you use. So you're good either way. Does that sort of answer your question? Okay. So let's talk about the door. So think about opening a door. When you go to open a door, the first thing I want you to think about is, where are the doorknobs? Where is the handle on the door always?
Mine's in the middle of the door.
Really? You've got a middle of the door one?
I do.
Wow, that's kind of rare. It's more old-timey too. Do you live in an old place?
It's pretty old. It's probably 70s, I would say.
Okay, well, so as someone born in the 70s, that's not old. But but if you think about it, usually they're not in the middle of the door. I mean, they're in the middle of the door up and down. But think about what the axis of rotation. In fact, you know what I'm going to do? We're going to go mobile here for a second. Let me mute this one, turn on my other one. We're going to go for a walk. Because I happen to have a door real close by here. Okay, so can you guys see the door?
Yeah.
All right, so if we look at the door, you'll notice the hinges are over on this side. And where the hinges are, that's your axis of rotation. We're rotating about that, right? Because as I spin this door open and closed, it's rotating about the axis that contains those hinges. So then if we look at where the doorknob is, notice that the doorknob is all the way over here by the edge of the door. So let me turn this thing sideways so we can maybe see a little bit more of the door. Back up a bit. Okay, so now we can see R. R is going to be the vector that goes from over here all the way to the doorknob. So that's R. Now, when I apply a force, my force vector is going to be coming from either into or out of this, depending upon what I'm doing. If I'm opening the door, it's a pull. So my force vector is pointing this direction. If I'm closing the door, now my force vector is pointing that way because it's a push. Right? But either way, it's coming into this point. So first of all, think about how this applies with the formula R times F times sine of theta. If the doorknob is on the far other side, we just made R large, which means we're giving more torque. More torque means more ability to turn. So when Bradley mentioned something about having the doorknob in the center, and real quick, Bradley, is that what you meant, like center, like here center?
Yeah.
Okay, that's what I thought.
Yeah, I would say it's, yeah, I'd say it's like right there.
Okay, I just wanted to make sure because that's what I thought you meant. So in that case, that's a much smaller R, which means it's going to be harder to open and close the door. So I want you to notice this the next time you go to open a door, every time you go to open a door, go look and see where the handles are. And most of the time, handles are on the far other side just because that's increasing the amount of torque. Okay, so R matters in terms of torque. I can also increase torque by increasing F, which means the amount of force I apply, right? And this would be why, like, you can slam a door. If you push really hard, it will rotate quickly, right? If I push just a little bit, it goes slowly. Same thing with pulls. So that's where F comes into play. But the part that gets kind of curious, and sometimes people go, well, then why do you need a cross product? Why do you need that sine business? Think about this. So we already saw that you get most torque if you are perpendicular. So if we come back to the door, let me show you here. So perpendicular is me pointing directly in, pushing directly into the door. Now I can apply the same force, but in a different direction, and I don't get nearly that much turn. If I change the angle, like let's say now we're going to kind of come here from the side. Now as I push, I'm not getting nearly as much rotation because a lot of my force is being put into pushing the door towards the axis. And in fact, let's see if I can do this without hurting myself because I've never tried with the camera. Okay, so you can all see me and you can see the door. I'm going to apply a force into the door, but I'm going to go straight in to R. Okay, so I'm just going to basically lean against the door. You can all see it, right? And I'm leaning. I'm actually putting my weight into it and I'm not getting any rotation. And that's because my force vector is pointing in the same direction as the R vector. technically they're opposite directions because I'm pushing. But even if I was pulling, here I'll switch to a pull, and you notice it's not rotating. That's because they're parallel. And that angle now is either 0 or 180 degrees. And either way, the sign ends up being 0. So it's not just magnitude of force, it's where that force is being applied and how we're applying that force, which direction we're applying it. So it turns out that it's way more complicated than just an acceleration, right? And a regular old force, because a regular force, we don't care what direction it is relative to anything. We care about what direction it's coming from because that's how it's going to set up our acceleration. But that's it. So we got to have a cross product, and that's our formula. All right, now let me get this set back up. All right. So torque is going to take the place then of force. Everywhere we had force before is now going to be a torque. If we want to create rotation, we have to have unbalanced torque. Just like if we wanted to have motion, we had to have unbalanced forces. When it comes to figuring out how much rotation we get or how much change in rotation we get, instead of using Newton's second law, good old F equals ma, we're going to use an angular equivalent of Newton's second law. Can you guess what that's going to look like? Instead of F equals ma, what would the angular equivalent be?
Omega. Or no, AC.
So we have three things we got to replace, right? Because now it's not force, now it's not mass, and now it's not linear acceleration. So what we're going to have now, if we go back to Newton's second law, so in the linear world, it was F equals ma. But now when we go to rotational, it's going to be torque is equal to I times alpha. So Victor just put fish times I, right? Yeah, so that's our little fish times I. So torque is going to equal moment of inertia times alpha. So think about how this is all playing out. Torque is the ability to cause something to rotate, just like force was the ability to make something move. The moment of inertia is how resistant to that move, that rotation, this object is. Whereas mass was the resistance to linear motion. And then alpha is going to be an angular acceleration. How quickly is our angular velocity changing? As opposed to A was how quickly our linear velocity was changing. So if you think back to all the problems you did back in first quarter physics, trying to solve things like, ooh, applying this force, what kind of motion do we get? We're going to do exactly the same thing, except now it's going to be, we apply this torque. What kind of rotation will we get? So it's not really that we have to learn anything new. We just have to realize we're doing this all rotating instead of linear. All right, let's take a real quick break. I got to go use the restroom real quick. So let me pause the video. All right, so I'm going to show you examples of how we do the same kind of problems that you did back in the linear days, where we look for sums of torques and then figure out what kind of angular acceleration we get, which then can tell us how fast things are spinning. We'll look at doing that torque argument versus an energy argument, because you kind of did that back in the day too, where sometimes you actually could get things faster by looking at kinetic energy as opposed to acceleration, yada, yada, yada. So let's do some examples, kind of playing with these quantities and seeing how everything works. Before I dive in though, any questions at this point? Looks like that's a no. Okay, so let's do this. Let's go to the board. So let's try this scenario. Let's say that we've got a big spool of wire, big spool of cable or something. And so what we're going to do is we're going to be pulling on this cable, causing the spool to spin or unwind. All right, so here's our big spool of cable, and we've got a cable that's coming out that we're pulling in this direction. So imagine that just wrapped around in here. Okay, so this cylinder, let's say that we know that it's got a mass of 50 kilograms, and it's got a diameter of 0.12 meters. All right, now we're pulling on this thing, let's say with a force of 9 newtons. So we're pulling on that 9 newtons. All right, so far so good. And let's
Yeah.
say that we pull this for 2 meters. So we're going to pull out 2 meters of wire. And so here's my question. How fast is this spool spinning after we pull out the 2 meters? And I think there's going to be a follow-up question to that. So not just how fast is this thing spinning, but also is how fast is the wire being pulled? So there's a two-part question. So the first one just is how fast is this thing going to be spinning? What's our rotational rate? And then also at that point, how fast is the wire being pulled? So maybe we can think that there's exactly 2 meters of wire. So as soon as that's gone, this is just left to spin. But I want to know how fast we're pulling at this point. Okay, so hopefully we're all good with the setup for this, what we're trying to do. So I'm going to start by looking at this as from the torque idea. We're going to look at the forces that are applied, what torques are applied, and then use that to calculate alpha. And then we'll look at it from an energy argument. All right, so first thing I want to do is draw a free body diagram. Let's put all of the force vectors in here that are acting on this spool, because every one of those forces can be applying a torque. How much torque? Well, it depends on the actual orientation of it, where it is, how far it is from the angle of rotation, or from the axis of rotation, what angle, so on and so forth. Okay, so you guys are smart. I know it's been a while, but let's do this. Tell me all the forces that are being applied to the spool right now. Okay, so Victor just chimed in with gravity. Good. That's one that we know is always there. So let's put gravity in here. I'm going to draw this again with just the forces. So where is gravity going to apply? Where do we put that vector?
Downward.
Okay, it's going to be downward. Where's it located?
Like on the side of the, like right on the side, I think.
I was
So on
thinking
the
the center
side,
of
you mean like
mass.
here,
Um,
over there?
yeah, yeah. Maybe more on the other side. Like,
Okay. Victor just said down the middle. So you remember that conversation we had last week about center of mass? This is where we're going to use that, because gravity applies as if it's in the center of mass. So if we assume that this wheel is evenly distributed in terms of its density, the center of mass is smack dab in the middle.
okay, I see.
So there's our gravity vector. And you can see why this matters now, why it matters where it's applied, because that's going to determine our R. So there's one of them. There's gravity. And this is where it gets a little bit different than before, because you may remember when you did force diagrams before, you just drew the arrow pointing the right way, and you didn't care about exactly where it was located. And that's true for, for linear quantities. But for rotation, we need to know exactly where it is. Okay, so we have gravity. What else? Okay, so Victor just threw in pulling force. So yep, let's put that one. Now that force is going to be at the top of the spool, call an F, that's pointing to the right. All right, so we're pulling on it. Gravity's trying to pull it down. Any other forces?
Friction,
Torque?
maybe.
Okay, so I heard friction, maybe. We're going to assume no friction. And there was
Torque?
somebody else saying something on top of the friction as well.
Bradley said torque.
Okay, so torque is going to come from our forces, but let's just talk forces. There is one more force, and it's one that lots of times we forget about.
Is it potential energy of the wire itself before it's pulled?
Normal force?
Okay, so it's not potential energy, because energy is a different thing. But then I think that was that you, Ian, who just said
Yeah.
normal force with the question mark?
Well, no, not question mark, normal force.
Okay, normal force. Yeah, there's a normal force. There is a normal force, because think about how this is drawn right now. If these were our only forces, what would happen to this spool? And don't talk about spinning, just like in terms of linear
Fall
motion,
down.
what would happen to it?
Yeah, I'd fall down to the fourth quadrant.
Okay, so it would get pulled over this way, right? By the friction or the pulling force. It would go down because of gravity. So like Bradley said, it would move in the direction of the fourth quadrant. But it doesn't. We've got this thing rigged up on, whatever, some kind of a stand so that it's not moving, which means there has to be another force that points up and to the left. And that normal force, again, is going to act as if it's in the center of mass. But so I'm just going to put it here with an N. So this has nothing to do with rotation, and this has everything to do with just linear motion. We know that these forces have to balance out, or else it'd be moving on us, and it's not supposed to be moving, it's just spinning. So there has to be another force that balances it out. Okay, so we have three forces. Now what we need to do is look at the torque for all three of those forces so that we can get a total torque for the entire object. All right, so I'm going to erase a little bit here. We know the questions that we're trying to answer. We got the information written somewhere, so let's get this out of the way here. All right, so for each of these three forces, we need to know two things. One, how far are they being, how far away are they at their point of application, and how far are they from that axis of rotation? And then what angle do we have between that force and that radial arm so that we can calculate that torque. So let's start with the spool being pulled by this guy that was 9 newtons. In terms of how far away it is, its moment arm is this guy right here. We're going to go run from the center, the axis of rotation, up to where we're applying that force. So I told you that this thing was 0.12 meters in diameter, which means that radius is 0.06 meters. Okay, so far so good. So now let's figure out what the torque is due to that one. So we'll call this torque number 1. It's going to be 9 newtons times 0.6 meters times the sine of the angle in between them. And since it's a right angle, sine of 90 degrees, so that's just going to equal 1. So this is 0.54 Newton meters. Not nanometers, Newton. So notice that torque has the same units as joules. Just happens. There is no like physical reason. So are we good with that one? The torque due to us pulling on the wire? Thumbs up?
Yes, thumbs up.
All right, so let's go to another one. Let's go to gravity. Okay, so gravity's pulling down. In terms of the magnitude of that force, I told you that this thing weighs 50 kilograms. So G is going to be 50 kilograms times 9.8 meters per second squared. So that's 490 newtons. All right, so we've got 490 Newton force. So now we need to multiply it by its radial arm. So what's the magnitude of R? So Victor just said the same again, 0.6. What do you guys think? Although now we just put a negative with a question mark. Well, let's think about this. Where is gravity being applied? It's being applied at the center of mass. Where's the axis of rotation?
Same spot.
It's at that same spot. So that means that R is actually 0. This would be like trying to open the door by applying a force at the hinges. You're never going to be able to do it. So for this one, we'll call it torque 2. Well, it's 490 newtons times 0 meters. So it turns out that gravity is not creating any torque. Does that feel weird?
Yes.
Okay, so Bradley says yes. So here's what I want you to think about. Suppose that we're not pulling on this wire. Okay, we're not going to pull on the wire. The spool is just sitting there. Is it going to rotate? No.
I guess not.
It's just going to sit there. Even though gravity is pulling down on it, it's not going to rotate because that gravity is going through the center of mass. Now, if that center of mass wasn't at the axis of rotation, then you would get rotation. And that's what happens when you have some funky shaped object that's falling, for example. It'll rotate until it gets such that the center of mass is directly in line with gravity. And we'll talk more about this later when we talk about equilibrium. But in this case, yeah, there's no torque due to that. Okay, so there's torque number 2. So then torque number 3 is going to come from the normal force. So if we wanted to calculate that normal force, we'd basically just have to take these two forces, use their components. That'd be the components of the normal force. But let's just jump ahead to this normal force, again, is being applied at the center of mass, because that's where we've got this thing anchored to move. So since it's at the center of mass, it's at the axis of rotation. So R is going to equal 0 again. So torque number 3 here is also 0. So from these 3 forces, only one of them actually applies a torque. And it's the force of pulling on the wire. So you're going to have to do this every time. Every time you have one of these problems, you need to go force by force and look at each one of them and figure out what their torques are. And now we can add them all together. The other thing that I'm going to warn you about when you have more than one torque, and we'll see this, I'll do another example where we have a bunch that we calculate, you have to pay attention to, are they causing clockwise or counterclockwise rotation? Because if they are trying to rotate in opposite directions, they're going to cancel each other out, right? One will be positive, the other will be negative. If they point in the same direction, you just add them up. So you do have to watch out for that when you have more than one. But we only have the one, so we're good to go. All right, so now let's see if we can figure out the angular acceleration, alpha, because we've got torque. All right, well, let me write this up here. So we've got our torque. The total torque is 0.54 Newton meters. So if I want to find alpha, because remember what we're looking for is how quickly is this rotating, which means we need to know an omega. In order to get an omega, we need to know alpha. So we're going to use Newton's second law, and that is that the torque is equal to I times alpha. So alpha is going to be torque divided by our moment of inertia. So we got to calculate moment of inertia. Well, this is a disk, so we already know its moment of inertia is going to be mr squared. We know its mass was 50 kilograms. We also know its radius was 0.06 meters. It's 1/2 mr squared. Sorry about that, for a disk, it's 1/2. So we're going to take 1/2 times 50 times 0.06 squared. And what we get is that the I is equal to 0.09 kilogram meter squared. So now we can actually calculate our alpha. It's going to be 0.54 Newton meters divided by 0.09 kilogram meter squared. And what we're left with is 6 radians per second squared. So just notice that the units, the way they work out, newtons have a kilogram that cancels. It's also got another meter from the meter per second squared, so the meter squareds go away, and you're just left with your second squared. So we have constant alpha, which means we can now get our omega if we go back to one of those kinematic equations. So remember that huge set of kinematic equations. We want to get
Yeah.
an omega final. And if you think about what we know that we've got an alpha. We also have an omega initial. Because what was our beginning angular velocity?
Zero.
It was 0 because it was stationary. So now we just need to figure out one other piece of information, like either time or a change in angle or something like that, and we're good to go. Or alternatively, if we want to find omega, we can find v. Because if we have v, we know how to use v equals r omega. Well, I suggest we find v. Because the one other thing that we know that we haven't used yet is the fact that we pulled out 2 meters of wire, and 2 meters is a distance. That distance, that's a linear quantity that we can then use the linear kinematic equations. So let's do this. Instead of having just alpha, let's find A. Let's find the tangential acceleration, because that equals r times alpha. So we know the r, 0.06. We know our alpha is 6 radians per second squared. So this is 0.36 meters per second squared. So that's our tangential acceleration, which now if we go back to the kinematics, we've got, in this case for the kinematics, we've got v initial is 0 because the wire wasn't moving at all. We've got A, that's a constant 0.36 meters per second. And we have a change in X, which is 2 meters. And that's enough for us to find the final velocity, because we can go to the formula that was V final squared equals V initial squared plus 2A delta X. So V initial is 0, so we get V final squared is 2 times 0.36 times 2. So that's V final squared is 1.44, which tells me that final velocity is 1.2. So we're pulling on that wire, and after 2 meters have come out, that wire is moving at 1.2 meters per second. Well, we still haven't answered the question. Because the question, well, I guess, did we answer the second part of the question? The second part of the question was how fast is that wire moving? So we got that. But the other question was how fast is the spool spinning? So that's omega. So we still need to figure out omega. So let's do that up here. So we know that omega is related to V by the formula of V equals R omega. So omega is going to be V over R. So omega final is going to be 1.2 meters per second divided by 0.06 meters. Which gives us 20 radians per second. So by pulling on the spool with a force of, what was it, 9 newtons, As soon as 2 meters of that wire come up, we're up to a rotational rate of 20 radians per second, which is pretty fast. Because again, remember, one full rotation is around 6 1/4 radians, so 2 pi. This is like 3 revolutions a second just by tugging on it. So a real similar approach to what you did when you were just doing linear quantities. We just have to, well, the complexity here comes from the fact that now sometimes we need to go from angular to linear, linear to angular, one way or the other. So this is definitely one where the more you practice, the easier they'll come. But this is also where a really good formula sheet comes in handy. Don't just write a formula down, but make sure you understand what the different things mean. That'll help you out. So I want to show you this same problem, but attacking it from an energy argument, just so you can see how that goes. But before I do that, any questions on this? All right, so hearing no questions, let's do the same thing, but from an angular energy kind of idea. So again, I want to figure out what the final omega is, how fast it's rotating, and then we can use that to figure out how fast the cable is moving. Okay. But again, we're going to look at kinetic energies. So let's think about the initial kinetic energy. And of course, this is rotational because the object itself is not moving. The spool is not moving. Let me write here, rotational. So the initial kinetic energy is 0 because it's not spinning. So then what about the final kinetic energy? Well, we know that that's equal to 1/2 I omega squared and so in order to figure this out, we'd need to know omega. Well, we're going to use this actually to find omega because we're going to figure out how much work is done, what that change in energy is, and then go from there. All right, so how are we going to get that? Well, let's just do this. We know that our work is the change in those kinetics. So the work is 1/2 I omega squared. Is a capital W, I apologize. So if I want to solve for omega, it's going to be the square root of 2W over I. Now the I we've calculated. You remember that was that 0.09. So we need to figure out how much work is done. Well, let's go back to linear ideas. How do you figure out work?
Force time displacement.
Okay, so it's going to be a force times displacement. So let's think about the work being done by our pulling force, right? We know how strong that force is. How long do we apply that force? Over what distance? Good, Victor just typed in 2 meters. So if we want to look at the work, that's going to be our 9 newtons times 2 meters. So the amount of work that was done, it was linear work. But that linear work is being done to change rotational kinetic energy. Had this spool moved as well as rotated, we would have had to figure out how much work goes into the pulling, how much goes into the rotating. But as this is, it's all rotation. Okay, so let's put this in here. So we're going to get the square root of 2 times 18. And then our moment of inertia was the 0.09. You do that calculation, and you end up with 20 radians per second, which, if I recall correctly, was actually the same thing that we found last time, the other process. We got our 20 radians per second. And then from this, we can get our V, because V is equal to R omega. And we end up with our 1.2 meters per second. So there were actually 2 different approaches to get here. One was looking at torques and spinning and all that. And then the other one was actually just done by using the energy. I would argue the energy argument was a little bit easier here. But I know you've seen examples of this with linear quantities, where sometimes the linear quantities, trying to balance all the forces, and then everything was a lot more complicated than just going to an energy argument. So you're not going to find anything different when we go to rotation. Same kind of story. Sometimes one is easier than the other. It's just a question of which one you want to do and which one you feel more comfortable with. All right, so questions on this one? All right. Well,
That's
then
a lot
we'll
of
go ahead
work.
and. Oh, I'm sorry. What was that?
I was just saying it's a lot of work.
Yep. Hold on 1 second. Well, I think there was a knock on the door, but it was actually for next door. But yeah, there are a lot of steps here. There are a ton of steps to try to do these problems. And I wish I could tell you that there's a fast way. Oh yeah, this is just how you do it. No, it's what information is given, which of these things do you want to use? But hopefully you're seeing the parallels between this rotational stuff and the linear. Because
Yeah, I do see that.
And that should make you feel a little bit better, because we're not really doing anything new. We're just applying it to the idea of turning as opposed to moving. But even in this example, you can see how they're kind of meshed together, right? We were pulling that wire linearly. There was linear motion that led to rotation. And you can actually have the opposite, right? You can have rotating that leads to linear motion. And in fact, that's one of the reasons why we use rotating. Right? A great example is your car. Your car is all about using rotation to make linear motion. Like if you think about how your engine is set up and everything, it's really just something spinning around because the pistons are pushing it. And yet somehow that rotation eventually transfers down to rotation of the wheels, which then eventually leads to movement of the car. So we can't think of these as 2 separate things. I mean, they are. Rotation is different than linear motion, but they work together. They combine together all the time, and we use one to make the other happen and vice versa. Okay, so the best advice and kind of rah-rah I can give you is don't treat this as a separate thing. You're going to attack these problems the same way you've attacked the other ones from first quarter. It's just now we're using angular quantities instead of linear quantities. And the one thing that might happen is you might have to relate them, but the equations that relate them are really easy. They're all the same form. S equals R times theta, V equals R times omega, A equals R times alpha, right? There's a nice simple relationship between all of them. All right, well, let's do another problem where we have some torque, a whole bunch of torques, and we're going to go ahead and combine the torques and figure out what the resulting torque is when we have a whole bunch, okay? So let me go back to the whiteboard. All right, and now here's what we're going to do. I'm going to give you a bunch of forces that are all being applied at different places. And we're going to figure out what the total torque is. And then we're going to use that total torque to determine what kind of angular acceleration we have and what kind of rotation is occurring. So I'm just going to give you a grid, good old coordinate system here, and we'll apply some forces. And let's say that the axis of rotation is going to be the origin. So we're going to be looking at doing things through the origin as the rotation. So maybe we've got just some sort of big blobby object, and we're going to apply some forces to it. So let's apply a force out here. Let's say that this force is 5 newtons. And I'll even tell you that this angle right here is 30 degrees. Okay, so that's one of the forces that's being applied. There's going to be another force over here. That's going to be in applying a force. Let's go with this is 3 newtons. And it's pointing directly to the left. Let me give you 2 more. Let's go with one right here. That's applying a force of 4 newtons. And I'll tell you that this angle is 20 degrees. And I think that's enough. We'll just use those as our 3 forces. Now, I need to give you a little bit more information because we don't have quite enough. We need to know where these things are. Okay, so that one is just going to be at 0, 1. This one's going to be at 3, minus 1. And let's say this is at minus 4, minus 2. So 3 forces. So here's my question. So A is, what is alpha? And then the second question is, which direction? So is this thing going to be rotating clockwise or counterclockwise? So alpha will tell us how much it's rotating, how much that angular velocity is changing, but I still want to know which direction. So are we clear with what we're trying to do? Hopefully. So yes, Victor, X bar and Y bar, we're going to say for the sake of everything that it is at 0, 0, so we don't have to worry about gravity. But you're right, because if gravity, if that wasn't the center of mass, then wherever the center of mass would be, like let's say it was here where my finger is, then that gravity would be pointing down and it would be yet another force. But we're just going to assume that this rotation is about the center of mass, so we don't have to worry about gravity. So only these 3 forces. Whatever's causing them, those are the only ones. All right, so just like before, let's find the 3 torques. Let's find a torque 1, a torque 2, and a torque 3. We'll figure out how big they are, and then we'll figure out whether they add together, whether they build upon each other, or whether they cancel each other out. All right, so let's start with the one that's up above, because I think that might be the easiest. So we've got its magnitude is 4 newtons. What about its radial arm? So the radial arm goes from the axis of rotation to where that force is applied. So that's just going to be this guy right here. So for torque 1, the magnitude of our force is 4 newtons. The radial arm is 1 meter. We're going to go with these things, the units are in meters. So it's going to be 1 meter. And then we need the sine of the angle in between them. So what angle are we going to use? All right, so Victor just threw in 20 in the chat, and that's exactly it. going to be sine of 20 degrees. Because if I were to put these so that they're emanating from the same point, 20 degrees is the quantity. So that's going to be torque number 1, at least its magnitude. So let's go ahead and calculate that, and then we'll talk about what direction it's pointing.
So
you do 4 sine of 20.
why
I'm
didn't
sorry,
you
go ahead,
use
Brad.
why didn't you use radians?
Because I'm in physics class.
Okay.
No, okay, so all I'm doing here, since I'm just calculating the sine of that angle, it doesn't matter if I'm in degrees or radians. Where it does matter is if we're actually calculating omega or alpha. So since I'm not doing that, I don't need to be in radians. You'll get the same number if you put in the radian equivalent, right? 20 degrees is the same as pi over 9. So you do sine of pi over 9, sine of 20 degrees, you're going to get the same thing. So that's why it doesn't matter here, because we're putting it into one of the trig functions. As opposed to like s equals r theta, since there is no trig function, those things we need to be in radians.
All right, thank you.
You're welcome. All right, so this gives me 1.368. So I've got 1.368 Newton meters of torque. Now, before we calculate one of the other two, I want to know which direction is this torque pointing. Is it causing clockwise or counterclockwise rotation? You got a 50-50 shot. What do you think? Clockwise or counterclockwise?
Counterclockwise?
All right, so counter. Victor agrees. Ralph says clockwise. We have a bunch of people who have fallen asleep. Oh, okay, there's Caesar saying clockwise. Well, let's use the right-hand rule. So we're doing R cross F. So you want to start with R. So R is pointing up. And I want to rotate towards F. So my force is going that way. So I'm going to rotate this way. So that's pointing this direction, which is showing counterclockwise rotation. So that force right there, so when I'm calling force number 1, is trying to make this rotate clockwise. Or sorry, counterclockwise. So I'm going to put below this counter. So this is going to tell us this one's trying to go counterclockwise. All right, so there's torque number 1. So let's go to torque number 2. I'll just call torque number 2 this one next to me. So let's look at torque number 2. So this time, here's R. So if I want to calculate this torque, again, I need the magnitude of the force, which is 3 newtons. But then I also need the magnitude of R. So this one, we're going to have to use a little trig, well, Pythagorean theorem. The R is going to be the square root of 4 squared plus 2 squared, right? Because we're out here 4 in the X and 2 in the Y. And then we're going to need the sine of the angle in between them. So I'm just going to call that theta for right now. So this is going to be 3 root 20 times the sine of theta. Uh-oh. How are we going to figure out theta?
Sine inverse.
Okay, so let's definitely use an inverse trig function. No doubt about it. Let's go back and look at this triangle right here. So if I want to know the angle in between them, this one's good enough for theta, right? I know that it's actually in the opposite direction of this guy, but in terms of the magnitude, that doesn't matter. And if we think about this, we know the sine of that is its opposite over its hypotenuse. So check this out. Its sine is going to be 2 over root 20. The root 20s cancel. And we're left with 6 Newton meters. How's that for a trick? Notice we didn't actually calculate what theta is. I have no idea. But it turns out I didn't need to, because I could just use the geometry of this picture to get rid of sine of theta. All right, so there's torque 2. So what about this one? Which way is it trying to go? Clockwise or counterclockwise?
I say counterclockwise.
All right, so counterclockwise. Ralph says neither. So does Victor. Well, let me first just answer the neither. It is going to rotate. It is going to cause rotation because this is not equal to 0.
Actually, I think it's just clockwise.
So let's go with the right-hand rule. Remember, I need my palm, my hand lined up so the palm's in R, and then I need to rotate towards this guy, F. Okay, well, in order to do that, I got to turn my hand. I can't do it this way and rotate. So it's actually trying to cause a rotation clockwise. So I'm going to put this up here. Torque number 2 is 6 Newton meters, but this one's going to be clockwise. Right? Think about it. If this is my axis of rotation and I apply a force this way, it's going to try to turn it in a clockwise direction. And even though it was a smaller force, it's applying way more torque than number 1. And that's because it's so much further away. Square root of 20 is significantly more than 1. So we're applying a force further away, which is causing more angular acceleration. All right, so there's number 2. So let's go to number 3. So number 3, same kind of story. So again, we've got our force is 5 newtons. We've got our radial arm. The moment arm, if we use the Pythagorean theorem, it's the square root of 3 squared plus 1 squared. And again, times the sine of the angle in between them. So this is going to be 5 square roots of 10 times the sine of theta. So what's theta?
It's square root of 10 over. Wait, actually, we know that one, right?
So we've already got the 30 degrees here. Turns out it's not 30 degrees. Because that 30 degrees, since that's 30 degrees from vertical,
So it's negative 60.
Negative 60.
I think so.
Victor put up 360 minus 30, so 330. Well, this is the trickiest, because if we want to think about this angle right here, it's the same as that angle right there. And the problem is, since this is offset from this guy being horizontal, we're gonna have to use a little bit of trickeration. So this was 30 degrees, which means, let me draw this picture of this geometry a little less cluttered. I'm gonna move it over here. So here's what we've got. Here are the fake axes from where this one was coming down. And that guy was 30 degrees. Now, the other one, I'm going to exaggerate it a bit. It's coming in like that. So what I really want is this entire angle, which is going to be the 30 degrees plus the 90 degrees plus whatever this angle is. So let's think about this angle back on this picture. That's that one. And that I can get. Like, for example, I can use inverse tangent. So let me call this guy phi. I know the tangent of phi is equal to 1 over 3. So equal to 1/3. So then theta is going to be 120 plus the inverse tangent of 1/3. So that 120 was this 30 degrees plus the right angle, that's the 120. And then the inverse tangent of 1/3 is giving me this guy right here. So this is the most challenging thing when it comes to actually finding torque, calculating it, is actually determining what that angle is. Because sometimes you have to pull tricks like this.
And you use alternate interior angles or congruent to do so?
No. I'm not using anything about any tricks of geometry other than I'm breaking this angle into the 3 pieces.
Okay.
Because this guy phi is not 30 degrees. It's not related to this one at all. It solely just comes from where this force is being applied. I don't know, did I answer that question okay?
Yeah.
Okay. Because if I do the inverse tangent of this, I get 18.43 degrees, which then when I add that 120 brings me to 138.43 something. So this guy is going to be 5√10 times the sine of 138.43. So then if we go ahead and figure that out, I get 10.5. So we get 10.5 Newton meters. So this is the biggest one by far. But again, it's the largest force and it's fairly far away. So there's our tau number 3. It's 10.5 Newton meters. So again, which way is it trying to rotate? Is it trying to go clockwise or counterclockwise? So Victor just put in clockwise. You guys agree?
I'd say counterclockwise.
All right, so Max is going counterclockwise. Imagine there were no other forces. Caesar just said clockwise. So imagine there are no other forces. I'm trying to rotate here. I apply a force this way. Which way is it going to want to spin? It's going to want to rotate clockwise. And if you do the right-hand rule, again, line this up in the direction of R and then curl towards F.
So I did it with the left hand.
Ah, that'll do
That's
it to
why.
you. Yep, if you
That
use the
makes
left
sense.
hand, the left-hand rule is going to give you the opposite direction. Okay, whew. So we've got our three forces that gave us our three torques, and we just calculated them all. And so you notice we have two that are going clockwise and one that's going counterclockwise. So in terms of which direction it's going to go, it's just a question of which direction has more total torque. And you guys can see pretty easily that that's going to be clockwise. So the end result of this is that we're going to get clockwise rotation. Right? We've got a clockwise torque. And in terms of the total magnitude, it's going to be 10.5 plus 6 minus, I'm just going to round that to 1.4. So you notice I'm subtracting the one that's going the opposite direction because it's kind of fighting it. So that's going to give us 15.1. So we end up with a total of 15.1 Newton meters of torque that's going in a clockwise direction. So if we wanted to figure out what alpha is, figure out how much angular acceleration we have, it would just be a matter of dividing this by the moment of inertia of this object. Again, I don't know what that is, but if it was given to me, I'd just divide it out. And then once I've got that alpha, then I can have all kinds of fun and figure out omegas and energies and all that good stuff. All right, so definitely a complicated question, even though on the surface it didn't seem like it was that big of a deal. And really the most complicated bit was this third one, just because neither the force nor the radial arm was pointing along the axes, right? For this first one, the radial arm was on an axis. For this one, the force was on an axis. So those made finding the angles a little bit easier. When neither one of them does, it sometimes requires more work. All right, so we good for that-ish? All right, thanks for the thumbs up, Max, I appreciate it.